So I want to spend a little time talking about the Navier-Stokes equations. When you hear the word Navier-Stokes or the term Navier-Stokes, what does that mean to you? Navier-Stokes. It's what? Well, it could be 3D. It's not necessarily only 2D. Continuity, if I said the continuity equation, what would that mean to you? Continuity. It's a conservation or balance principle. It's conservation of mass. Statement of conservation of mass. Navier-Stokes would be balance, or sometimes people might say conservation. Oh, what? Mass? No, that's continuity. What is it? Navier-Stokes. Don't check out on me. Come on. No? What is it? It's the analogy of F equal ma. It's the fluid mechanics F equal ma. So what is F equals ma? The name of it is Newton's second law, but what is it a statement of? How forces can change the momentum of a system, how it can change. So a lot of times it'll be the sum of the forces, time rate of change of some mv. Change of the linear momentum of the system. So this is Navier-Stokes is a linear momentum equation, linear momentum conservation. Some people will say that, but it's really not conserved. So I say a balance of linear momentum. So what can happen is if you have an imbalance of forces on the system, the forces typically you think of body and surface. And count for all the forces, and then there can be a net change in the momentum of the flow. Okay, so it's really a set of differential equations. So let's just jump into it. So what is this equation right here? It's a differential equation. Let's make sure we understand each term. What is rho? Density. What is v? With that is the velocity of the vector field. And what is del? Sometimes they put the vector symbol on del to emphasize, please treat that as a vector entity. But what is this del dot? That's this divergence, which is the partial with respect to x in the I, but you need to give it something. And then you have also the partial with respect to y, j, and the partial with respect to z, k. So that's why they put a vector notation on top. Sometimes they do, to emphasize, please treat it as a vector. I, j, k components. So this is the divergence of the rho v. This is an interesting term. You see this rho v grouping. What happens if I would have multiplied by a? What would that look like? Rho va, rho va. That sure does look like a mass flow rate, doesn't it? But if I multiply by a and I don't want to change the equation, maybe I divide by a. So when you see rho v, it's hard to get a physical sense of it, but it's really a mass flux. It's a mass flow rate per unit area. So this is the mass flow rate per unit area, which is a mass flux.
Or like the momentum per unit volume.
Yeah, you can also have momentum flow rates, momentum fluxes as well. That's right. You can have angular as well as linear. Okay, so this is the continuity equation, statement of the conservation of mass. Does it assume it's steady state as written? Does it assume it's steady state? There's a time derivative in there, isn't there? Does it assume any particular coordinate system, or is it written in a way that it could be expressed for Cartesian, cylindrical, spherical, Those are the three we use. There's other coordinate systems, but we just don't use them in engineering. Toroidal coordinate system. Forget it. I give up. I quit. But this is written for any coordinate system. It's not restricted to the Cartesian, but we often use Cartesian coordinate system because it's using vector differential notation, which is very generic. All right, what about this equation? Well, if that's the continuity equation, what do you think this equation is? The Navier-Stokes. And I know we have some of the terms jumbled up, but this is a pressure, force per unit area, gravity, what's that? Body force. And what is this term? Viscous. And so that, if you think of viscous, that'll be a surface. This will be a body, and this will be a surface. But that surface force from the pressure is normal to the surface, and for the shear force, the viscous term, it's a shear force to the surface. Okay, so these are all like the sum of the F's. And then what does it result in? Time rate of change of momentum of the system. So it can be swept in or swept out. Professor, we have this big typo. What is that big D? Is that a typo? No, it's not. What's the funny name of that derivative? It's the material derivative. That's right. There's a number of other names for it. Substantial derivative, total derivative, something. There's just a bunch of different names, but material derivative is a good notion. Okay. As written, is it for the Cartesian coordinate system only? No. They do assume by having this mu in here, it's Newtonian fluid, and they pull that mu outside. That term is a Laplacian. Otherwise, it's a little more complicated. But what we have is you always see it at this level for a Newtonian fluid. What does the Newtonian fluid mean? Well, the shear stress is proportional to the shear strain. You can write it in 1D, like partial of u with respect to y. That's a simple way of writing it, but it's constant through this proportional through this constant of proportionality known as the viscosity. And that viscosity doesn't depend on the rate of strain. How did they show it? As a shear stress as a function of, what did they use, eta or epsilon for rate of strain? It was a straight line, and this rate of strain is du dy, 1D. Okay. You can have shear thickening, shear thinning fluids, non-Newtonian fluids. There's plenty of them out there in the real world, but luckily air is Newtonian, and water, Newtonian, right? So a lot of the fluids that we use in engineering applications are Newtonian, or approximately close enough that we're going to treat them as Newtonian fluids. But a lot of times we do work with incompressible substances. So if it's incompressible, how does the continuity equation change? Yeah, you could see that you have the partial of rho with respect to time. If it's incompressible, that's 0, plus the divergence of rho v, the mass flux. But if rho is constant, then it can come outside. And then we just have that this is equal to 0. You can multiply both sides of the equation by 1 over rho to get rid of the rho. Multiply the whole equation by 1 over rho. And the left-hand side, or the right-hand side, is still 0, and the left-hand side becomes simply del dot V. All right. So the divergence of the velocity field is equal to 0. That's what's written right here. Okay. We just expanded out this material derivative term and really didn't change anything else over here. It's a Newtonian fluid as written up here. Let's continue on. So you can expand these, and they're in the equation sheet and textbooks, expanded in the Cartesian coordinate system. So this equation is the continuity for incompressible Newtonian fluid. Really, it's just incompressible. And then for a Newtonian fluid with that viscosity, you expand out the x, y, and z momentum equations, and you get all of these terms. And so it's nice to solve some problems where you would start out with a pretty large set of equations and then strike the zero terms and then reduce to a simple ODE maybe, and then solve that ordinary differential equation. Let's go ahead and do it for this problem. We have viscous liquid that flows down an inclined plane. So here's our plane. It's inclined with respect to the horizontal by an angle theta. And so here is gravity acting downward. And the liquid's going to just flow due to gravity down that inclined plane. The flow is steady state. It's fully developed. It's laminar flow. The thickness of the film is cap H, and the width in the third dimension is B. So let me try and draw here maybe as the layer of fluid. And since it's steady state, its thickness is H everywhere over that plane. And in the third dimension, B goes back. All right. Develop an expression for the velocity profile. What are they asking for part A? Velocity profile. Well, what's the velocity look like? At the plate down here, what is the speed of the fluid from the no-slip boundary condition? Where do you think the maximum speed is going to be located? At the top. And so what we do is we introduce a slightly changed coordinate system, x and y, so that things are aligned where the flow is only in the x direction, not kind of in the x and y, but only in that rotated coordinate system x direction. And we're looking for the velocity in the x, which we use the symbol u for, lowercase u. And that u is not a function of x, but it's a function of y. That's a lot to swallow. But that's what we're looking for. When they say the velocity profile, you say, oh, I know it's only one-dimensional. I'm going to rotate my coordinate system such that x is aligned with the plane. Now I'm going to be talking about not cap v with both ui and vj and wk, but I'm just going to be talking about u in the x direction. And it's a function of y, the distance from the plate out into the fluid, and it ends at y equal to h. I don't really need, I'm looking for u as a function of y between 0 and h. Yeah, I don't need it to go beyond h. True? So that's what we're looking for part A. Then if we get that, we can get part B and then part C. So what do? We have a rotated coordinate system. Hopefully you have a good image of this, because I'm going to go back to the previous equation slide with all of my differential equations. I'm going to say, oh, it's steady state, it's an incompressible liquid, and it's a Newtonian fluid. And so you say, here are my equations for conservation of mass, and then Newton's second law for how the momentum can change due to an imbalance of forces. And I say, okay, remember, anything with a W in it is 0, because it's truly a one-dimensional flow, and W is 0. There's no flow in the third dimension, so it's like this is 0, this is 0, because if W is equal to 0, then what's the first derivative of W equal to? 0. How about the second derivative of W equal to 0 as well? This whole equation just goes away. All right. I think I need to talk a little bit about these terms right here. Let me go back to my illustration. So if I have G, I need to decompose it into something in the X direction and something in the Y direction, true? So what I want to do is I want to put a little right triangle right there, and I want to talk about G in the Y and G in the X. And what is the relationship between this angle theta down here and that angle theta of that little right triangle? Are they the same? Are they the same? Okay. And so this, a lot of times we'll put G as a vector. Let me show this as a vector here. G as a vector is equal to G in the xi plus G in the yj. Okay, for this problem, what would be Gx equal to? G sine theta in the I. And then in the y, now this is in the positive x. Isn't the gravity pulling it in the positive x, making it, but notice I've got to take care of the negative sign in the y direction because y is going which direction? Up from the bottom plate up into the fluid, and G is coming in the opposite. So I'm going to put a negative G cosine angle theta. I paused. Did I do that right? So if we see G sub x, we know it's positive G sine of theta. If we see G sub y, it's negative G cosine of theta. Okay, good. Now that I've covered that, we can jump back here because we know what that Gx is and that Gy is. One of them's negative, one of them's positive. Okay. So let's continue striking all the W's. 0, 0. Did I get all the W's? Sometimes I like to even rub it out like so. I don't, it's like if W is equal to 0, I don't care what the other term is. 0 times something is 0. So it's out of here. Okay. Did we say it was steady state? Yeah, so I should get rid of that out of the momentum equation. And it's not, anything's not a function of z. So the velocities are not a function of z. All right. Now, talk a little bit about what this continuity equation tells us in its present form. It says that the rate of change of u with respect to x plus the rate of change of v with respect to y is equal to 0. Okay. Once we've gotten fully developed flow, this is a little bit of a concept. If I move and I say I want to look at the velocity profile at this location, will it be any different than maybe the velocity profile at this location? Or maybe I sketch out the velocity profile at location A, B, and C. Will the velocity profiles be any different if it's fully developed? That's a big conclusion. So if it's fully developed, is u could be a function of, in the most general case, it could be a function of both location x and y. But in this case, because it's fully developed, u is a function of y only. I mean, I could say look, u is a function of time, location, and y. And because it's steady state, it's not a function of time anymore, but only a function of x and y. And then you say, hey, it's fully developed. The way I've set up my coordinate system, it's only a function of y. So if u is only a function of y, tell me a little bit about the partial of u with respect to x. Do you see that? So now I jump back here and I say, this partial of u with respect to x, through a little bit of logic, is 0. From the continuity now, what about the change in v? I forgot, what is lowercase v? In the y direction. How does that change with respect to y? Well, from continuity, it must be 0. Okay, so I'm going to bring that over here for our illustration. So we have deduced from continuity the change in v with respect to y is equal to 0. Can you tell me what v is at y equal to 0? At the bottom plate. What is v at the plate? Isn't it 0? I mean, it's not penetrating the plate, or the plate's not generating fluid and throwing it out. No. So if I have a nice differential equation right here with initial condition, boundary condition right here, guess what the solution is? V at every location y, don't get too excited, it's pretty anticlimactic, is 0. You said, I think I could have figured that out. Well, we just did. So it's not like the fluid's flowing. Once it's fully developed, it's not like the fluid is flowing up or down in the y direction. It's only in the x direction. So now we can come back and we say, if v is everywhere equal to 0, and the change in v with respect to y is equal to 0. Can you tell me what the change in v with respect to x is? How about the second derivative of v with respect to x and the second derivative of v with respect to y? So we have a lot of zeros. V with respect to y, also v is equal to 0. V with respect to x is 0. You notice this two terms are multiplied. We're not saying u is equal to 0. We're just saying the change in v with respect to x is equal to 0. So what does the second equation, or the y equation, look like? The x, y, and z. The second equation is the y direction equation. We just get that the equation boils down to the change in the pressure with respect to y is equal to rho g y, and gy was negative g sine or cos. I think it's cos theta. Let's jump back here. Yeah, gy was negative g cos theta. Did I do that right? And you could say, well, what about the pressure at some location, either at y equal to 0 or pressure at y equal to h? Could I probably, I'm going to spend a little time here beating, the issues. It's not much here to get, but I'm just playing a little bit. So let's use this equation, which says that it's atmospheric pressure at y equal to h, at the outer edge of the fluid. And then I have this differential equation. You can solve for the pressure as a function of y. It's going to be the atmospheric pressure, and then you're going to go down by rho times the effective g cosine theta times the y, but we'll have to make this work where we have, I think it's h minus y. And let me see if that works out. When y is equal to h, that term goes to 0. When y is equal to 0, the pressure at the bottom is a little higher because of the rho gh of the fluid above it. So here you can solve for the pressure. I know I skipped a couple steps. You separate, integrate, and there you go. Okay? Okay, but we still haven't gotten to the main thrust. We basically use these two pieces in the the y momentum equation, and we're able to solve for something like the pressure is hydrostatic. Okay. Now let me go over here and go back to this first equation right here. Okay. Which terms did we not strike to be 0? We have, let's say, term A, B, C, D, and E. I'm going to pause. I'm going to leave this up here for a minute. I'm going to walk around the room, And I want you to take and write down the equation at that stage where we have just these terms. Don't forget the rho, okay? And don't forget the viscosity here and the density there. But I want you to strike the terms you think are zero, okay? And why? And I want you to simplify that equation some more. All right, my mistake. I should have done this. I should have said A, B, C, D, E, and F, because the gravity term, that G sub x is not zero. It's still something, right? And we want all the non-zero terms to remain in the equation. So let's do this together. How many people think that the term that I've circled here, A, is zero, drops out? Okay, why does that term drop out? Either U could be zero everywhere, or the change in U with respect to x is zero everywhere. It's the second part, isn't it? It's the rate of change of U with respect to x is zero. It's not. I'm not saying U everywhere is zero. That would be ridiculous. Okay, now B. How about the B term? How many people had B drop out? A couple. Okay, why did B drop out? It could drop out either because V everywhere is zero, or that the change in U with respect to Y is zero. But this time, the change in U with respect to Y is not zero, is it? But guess what V is everywhere? Zero. So that term B drops out. What about C? How does the pressure change as a function of x? Probably should have talked about that some more. How does the atmospheric pressure change as I go? Atmospheric pressure doesn't change at all, does it? The pressure only changes as a function of y. It doesn't change as a function of x. And so maybe there's more logic that I should have employed, but C is zero. D, the term that I should have labeled earlier, is not zero. It's staying in their equation. Okay, but E or F, one of those two terms is zero. E. Okay, why E? The second derivative with respect to x, once it's fully developed, it's zero. So we get a simplified differential equation that says that, let me see if I can write it like this. Minus rho g sub x was g sine theta equal to mu second derivative, and I'm going to move from a partial to an ordinary derivative because u is only a function of y. We discussed that. So there you go. There's our second order differential equation. This is ODE. Does that equation look good? How many boundary conditions do I need? How many boundary conditions? 2, boundary condition number 1, and boundary condition number 2. Let me do this. I'm going to grab that now and move it to the other, if I can grab it. I'll move it back to the other slide. Let's do a copy. Come over here. I'm going to get rid of this, tuck it in here a little bit. Let's do a paste. And we'll put it right here. So now we can look a little better and say, okay, what is one boundary condition? I'm trying to solve for u, and we know that u goes as a function of y between 0 and h. So think about boundary conditions. u at y equal to 0 is equal to 0. And the next one's harder. U at y equal to h is, it's the derivative with respect to y of u at y equal to h, that's a different way of writing it, is equal to what? 0. So it's the slope. It's the slope. You may want to think about this. Say, okay, why does that have to be 0? Well, so if we have two fluids, okay, and the fluid A is exerting a shear stress on B in that direction, then equal and opposite, what about B is exerting a shear stress of equal magnitude in the opposite direction, B on A, true? Well, what's our fluid out here? Air. What's our fluid in here? Some sort of liquid. So you can think about, well, that air has a no-slip boundary condition, and it has to be flowing. If I wanted to sketch the velocity profile, it has to be flowing at the same speed as the liquid at that surface, so it has to have some sort of profile like this. You know, it's kind of like dragging the air along with it, true? And then you would say, well, then this exerts a shear stress, so we have the mu of the air times the du dy for the air at H plus, you know, just into the air. And that has to be matched by mu of the liquid times du dy for H minus. Okay? But we have the viscosity of air is much, much smaller than the viscosity of liquids. Hence, we basically let this be so, because of the small viscosity, even though you may have a dramatic change here, it's still approximately 0. There's a little bit of logic on that boundary condition out there. Okay? The air isn't sort of retarding the flow of the liquid at the top. Okay? But if you had two viscous, let's say I had two immiscible, meaning they don't mix, fluids. Here's a new problem. Insert new. In the cavity, and here is fluid A, and here is fluid B, and they're both pretty viscous. Well, then you're going to have some profile for the velocity profile of A, and it doesn't necessarily go flat right there. And then the velocity profile of B, and it doesn't necessarily go flat right there. And the rate of change and the rate of change gives you some extra boundary condition out there. But let's not get too worried about that. So, with these two boundary conditions in that differential equation, can you solve for u as a function of y? Let me pause, walk around, let me see if you can do that, okay? This is one of those where I know you can do it given the time. So let's just work it through it together. So what are we going to do? We're going to have, let's do the separate integrate once. Du dy is equal to negative rho g sine of theta over mu. That whole term just acts as a constant. And then you integrate and you pick up a y plus a constant of integration. True? So I separated and integrated once. And then I can apply this boundary condition. When I apply that boundary condition, what do we deduce about the constant c? What do we deduce about that constant c? That c has to be equal to rho g sine theta h divided by mu. That's what c has to be. True? Okay. And then we now ready to separate integrate again. We get u is equal to negative, I'm going to just pull out the rho g sine theta over mu, and then we'll have 1/2 y squared plus h times y at another constant of integration. Did I do that correct? And then let's apply this boundary condition. If you apply that boundary condition, what does it tell you about the constant c? Has to be 0. And now we just rewrite, and we get the u is equal to, depend where you want to put the negative, rho g sine theta over mu is a constant. And you're going to have, excuse me, we could put h, h y minus 1/2 y squared. I messed up a little bit. This was supposed to be a minus h right there. Okay, there you go. And that's a solution. That'll work. Okay, you test the solution, check your boundary conditions, and it works. Now, how about for part B? What is the volume flow rate per width? How do you calculate the volume flow rate per width? Well, they're asking for Q divided by the width is B. And how do I calculate the Q, the integral of U d A 1 over B. Okay, the integral U dA 1 over B. Let's do the integral. It's going to be U is a function of Y. You're going to integrate with respect to Y, and then you have Y times the depth. B gives you the per unit area, so the B's cancel. And so now I have to do this integral of, I can pull outside the constant rho g sine theta over mu, the integral of hy minus 1/2 y squared dy from 0 to h. Okay, so continuing that integration, rho g sine theta over mu, you have 1/2 h y squared minus 1/6 y cubed, evaluated 0 to h, and you get rho g sine theta over mu. 1/2 minus 1/6 is 1/3 of h cubed. So that's q over b 1/3 g rho g sine theta h cubed divided by mu. That makes sense? Is it boring watching me do that? Did you get anything out of that? And then for part C, sorry, I have to scroll up to see it, but let's go. We want the fluid shear stress at the plane surface. So how do I calculate that fluid shear stress at the wall? Is it the viscosity times du dy at the wall? Yeah, that's all we have to do. And we had the solution. Actually, you just take the analytic solution, differentiate it, and multiply by mu. So here's the analytic solution. So we're going to get the rho g sine theta over mu. Derivative is going to be h minus y, but we want to evaluate that at the wall, y equal to 0, so that goes away. And so we get that the shear stress at the wall is just rho g sine theta. The mu's cancel, surprisingly. Rho g sine theta h. Make sense? Done with that one? So let me try and recap. You have these differential equations describing fluid flow, continuity, and the Navier-Stokes. Conservation of mass, and then Newton's second law for a fluid. So you can set up and solve for many different types of problems. Where does this really come in handy? Well, we go back and think about our similitude we covered in dimensional analysis. We talked about you can develop links between prototypes, full-scale devices that have fluid flow is important to their behavior, and a model, something that you can test in a laboratory, often scaled, much, much smaller, put it in a wind tunnel. And we talked about the similarity being required. Geometric similarity, thinking about how the lengths have to work. You have to scale every length proportionately between the prototype and the model. Kinematic similarity, how the velocities have to scale between the two such that you get the same general overall pattern of the flow field. Streamlines have the same shape, things like that. Dynamic similarity, where you have the same relationship between the forces, such that the force that you measure on the test, on the model, can be infer the resultant force on the full-scale prototype. So you have some force ratio, velocity ratio, length ratio, and if that's right, then you can extrapolate measurements from a handful of measurements to a wide range of measurements, and that's what's done a lot in fluid mechanics. For example, remember their sphere? We said, well, the force drag as a function of the diameter of the sphere, the fluid properties, the approach velocity, the uniform flow field, and then we came out with, oh, we have a drag coefficient, C sub d, in dimensionless form. It's a dimensionless force, drag force, excuse me, is a function of, this is like pi group 1 and this is pi group 2, a property called the Reynolds number. We give it the Reynolds number, the name Reynolds number, and that's it. And then you can expect to have C sub d as a function of Reynolds number, and it's not going to be like 7 lines on here for the same sphere. It's going to be one line. And it doesn't matter how big the sphere is, and if it's in air or water or oil, as long as you've matched these things, and this is a classic example where it's pretty easy to do the matching. So it goes from a whole range of flows where you have very low Reynolds number. Low Reynolds number, it's viscous dominated, to high Reynolds number. You have a large wake region behind the sphere. It's a large pressure component to the drag force, etc. Well, what we can do if we have our differential equations, we can cast them in dimensionless form. And that's another way of seeing, oh, there's the Reynolds number. You can get it out of the differential equations. You don't have to, I like to think of the Buckingham pie is like you throw everything into a big bag. You ever did it? And then shake it up. Shake, shake, shake. And then reach in kind of like as a random drawing and pull out things. And if you get a pretty complicated set of parameters, you can get a bunch of different pairings and groupings. When you only have a few, like 5 parameters, you have 3 dimensions, you're going to get only 2 pi groups, and it's not too surprising what they are. But when you get more complicated systems, it can be like, how do you know that this is the best? Or it has a bunch of intuition or experience then that guides the person to represent the data this way or that way. But here we can go back to our governing differential equations, and we can cast them in dimensionless form, and we can see some of those dimensionless groups come right on out of the math. So you go back to the continuity and the Navier-Stokes. We're going to work with incompressible Newtonian fluid, simplify it as we just have seen, And if you introduce dimensionless variables, the easy one maybe is dimensionless velocity. So you take your velocity vector everywhere and you just divide by cap v. What is cap v? Maybe that's the approach velocity incident on my object that I'm studying in the wind tunnel. Cast the lengths. Each dimension is normalized by one length scale. And so that's the way you would write it in vector form. If you have a gravity vector, normalize it by the gravity. Maybe you just have to see that worked out. Those are the three easy ones. The little harder one would be this one for time. You want some dimensionless time. Well, you have to make up something that works. And what they've done in the textbook, and I'm following the textbook, is they have time, and you divide or multiply by the frequency. What's a frequency? Let's say something in my system is oscillating back and forth within the fluid, and it can be characterized by the frequency of its cycle, how long it takes to complete a cycle. And so wasn't the frequency in 1 seconds, like hertz? Okay, so you could see that that's now dimensionless. That's a dimensionless time. And another one, a little harder, is maybe not harder, but it's a little more complicated. It's dimensionless pressure, but we're not necessarily interested in the magnitude of the pressure. It's the pressure difference, because it's the pressure difference on the front side and the back side that make a net form drag on my object. So we talk about we're going to take the difference between some far away pressure, some ambient pressure from free stream pressure, but that would just be a difference in pressure. We have to normalize that by the maximum pressure that we might expect, some stagnation pressure minus the atmospheric pressure or free stream pressure. That will be a dimensionless pressure ratio, or dimensionless pressure difference ratio. How's that? With these, now you play the mathematician, and you could take that governing equation, that's the hard one, and cast it into this equation, and you'll pick out this dimensionless parameter, this dimensionless parameter, this dimensionless parameter, and this dimensionless parameter. Of the parameters A, B, C, and D, which one are you most familiar with? D. It's called the Reynolds number. And so the Reynolds number defined as that. Rho v some characteristic length over the viscosity mu. It comes out of the math. Before I get bogged down in the math, I want to sort of say, this is the ending. We'll do a few steps in it, but let's make sure we understand why this would be useful. And then we have another number, the Summer number, and it characterizes some importance of the gravity, the body force in the flow. Okay? The Euler number we have seen before. It characterizes that pressure difference. Let's think of that as our maximum stagnation pressure. It doesn't have to be, but it's P naught. Divided or minus P infinity. So we have, this is our pressure difference. And you normalize it by what? You could put a 1/2 in there or leave the 1/2 out, but it's rho v squared. That sure does look like our dynamic pressure. That would be bringing a fluid stream, fluid packet from here with speed v to rest. That would be an increase in pressure by 1/2 rho v squared. We've seen that a couple times. Okay, so that's our Euler number. And the Strudel number, it's characterized by this frequency of motion. A lot of times we don't have that. We have fluid flow in a pipe, and I'm not sort of wiggling the pipe with the constant frequency. Okay, but the book talks a couple of examples where you have biological systems and maybe a fish in these moving his fins at a certain frequency, and so that's a different number. So what you can do now is you can see out of this section of the textbook how some of these groupings of parameters naturally come about, especially the Reynolds number. Okay, let's take a look. What was all of this group over here? How would you describe that in our F equals? Isn't this our how the linear momentum of the flow is changing? Yeah. What about all of these terms? Those are our forces. We have this type of force on this one, viscous, body due to gravity, and this is our pressure forces. So these are our normal surface or perpendicular surface. And these are our shear stresses or shear forces acting on our objects. Okay. We already talked a little bit about the Reynolds number. If the Reynolds number is large, what does that tell us? Inertial force is much, much greater than viscous. And we'd anticipate, because inertial forces are much, much greater than viscous, that it would be more turbulent. And then how about if it's small? Just opposite. Inertial forces are small compared to the viscous, and you would expect laminar flow. So if I was to take this equation, this is our full Navier-Stokes. Before the full Navier-Stokes was developed, there was a simpler set of equations, and they neglected this term right in here. When they neglected that term right in there, what did they neglect? The shear stresses, the viscosity. It was frictionless flow. Frictionless flow. So if this is neglected, is that because the Reynolds number is high, or the Reynolds number is low for this term to be neglected? Just look at the term again. If Reynolds number is very, very high, if we would expect it to be the inertial forces much, much greater than the viscous, then if the Reynolds number is high, this could be neglected. If that's neglected, basically you're saying it's frictionless flow, or inviscid flow. And basically without that term, you have what they call not the Navier-Stokes equations, but a predecessor before it, the Euler equation. The Euler equations. Okay. So now let's take a look at, maybe I already did that one, let me see. Yeah, this is the Euler equation. It's when you have high Reynolds number. And this term right here, you can see it goes to the 1 over Reynolds number, this dimensionless Laplacian of the velocity profile. And then this would be negligible in the Euler equations. So this would be negligible. You could have some acceleration of the flow, but you would just have body and normal forces. Okay. Another one to note is what happens if you have creeping flow, creeping going very, very slow flow. What about creeping flow? Well, that would be the Reynolds number low. If the Reynolds number is low, 1 over the Reynolds number is important. Don't throw it out. If it's steady flow, then that whole transient term goes. That's 0. And so you would just have some sort of pressure around it, and you'd have this viscous term surviving in the Navier-Stokes. So what you have is the general equations, and you say, oh, for this type of flow, these terms drop out. For this type of flow, these other terms drop out. And then you can solve it. Now, to even take the simple case of a flow around a sphere, creeping flow, throw out the gravity, throw G out, just throw that out, right? And just have to try to get that you have high pressure and low pressure, and you're going around the sphere like that is a challenge. mathematically, analytically. It's very much a challenge. So what I'm going to do is just allude to you can solve these problems, but often you have to use sophisticated computational tools to solve them. Now, we're going to talk about external flow for the next, 50 minutes or so. And external flow can be studied by first looking at flow over a flat plate. So we're going to talk about flow over a flat plate and external flow for a while. Let me jump to another set of slides. Okay, so let's spend some time talking about external flow, and it's going to be a while before I get back to that flow over a flat plate and looking at the governing differential equations. Maybe I won't be able to do it today. It may be too much. But I really want to take a soft introduction to this chapter, this section of the textbook. So a bunch of simple questions. Flow fields over most bodies are complicated and cannot be solved analytically. Hence, often the solutions are based on correlations, based on experimental data. Do you agree, true, or disagree, false? I know it's a long statement, but it really is true. Fluid mechanics, we just have a few gems of solutions to a limited handful of flow fields and conditions. And for some of them, they're pretty complex, mathematically, even the analytic solution. And sometimes it's just easier to say, I'm going to apply numerical methods to it and solve it using computational techniques. Forget the analytic techniques because they're just so complicated. But this is definitely true. So throughout, you can think of there's just a handful of analytic solutions, most of the time computational simulation or experimental data. Compressible effects are negligible with minimal error when the Mach number is 0, Mach number greater than 0.3, less than 0.3, greater than 10, or less than a tenth. And such flows can be treated as incompressible with little loss in accuracy. This statement, I think, is directly out of the textbook. C. It's one of these numbers that you might want to just remember. Most people would admit when you have flow, and even for air, and the Mach number is less than 0.3, you could treat the air as incompressible. If you start getting air really moving, or an object really moving through the air, it would be, no, you need to start thinking about compressible effects and consider them, especially anywhere around a Mach number of 1. Okay. How fast is the speed of air at, let's say, 70 degrees F or 20-some degrees C? How fast is it? What is the speed of air? The speed of sound in air. I butcher what I say sometimes. I know what I'm trying to say, but how would you calculate this? What is the speed of sound in air so I can calculate the Mach number? I need to know that. What symbol do you want to use for the speed of sound? C. Square root K R T. So let's say you have a calculator. Who has a calculator? Let's make this calculation. So what is K for air? 1.4. R. It's 8.314 divided by 29, 28.97. So 8.314 divided by 28.97, the molar mass. So the R bar divided by molar mass. And now these are kind of interesting units. I need to worry about my units at this point. This is kilojoules per kilogram Kelvin. Kilojoules per kilogram. It's a kilojoule per kilogram Kelvin. And then I'm going to worry about my units in a second, but I know I need to worry about them. Let's put in our temperature in Kelvin. What's the room temperature, atmospheric temperature, close to 300, right? 298, something like that. If you want to put 298, put 298 Kelvin. So we see that the kelvins go, but what units do I want for C? Meters per second. So I need to multiply by unit conversion that 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram. And with that, we can now cancel. We'll get the right units. And so can somebody please tell me what the speed of sound is in air? Okay, what did you get again? 350 meters per second. Everybody agree? All right. Let's say I'm driving my car down the road. How fast do you drive? 70, 60 miles an hour? 60? Let's go 70. You're blowing away at 70 miles per hour. All right. What is your Mach number of the automobile flaming through the air? Well, I need to get that speed of my automobile in meters per second. So 70 miles per 3,600 seconds. A mile is 50 to 80 feet. True? And a foot is, however do you want to do it, 0.3048 meter. A foot, 0.3048 meter. What is you tell me, how do you do the meter and feet conversion? Look it up somewhere. Let's look it up. Did they have it on the front of the textbook? And what is it for a meter? 0.3048 meters. Yep. So 70 mile per hour is how many meters per second? I'm sorry? You got to give it a little louder. Meters per second. So you are really ripping down the road. You can stick your hand out the window. You can feel the effects of the air on your hand at 70 miles per hour. What is your Mach number? Is 31.3 divided by 346. Do I need to consider compressible effects of air flowing over and around my automobile? They can be neglected. They can be. But if I have in a rocket or an aircraft that's going super fast, then I can't. All right. So there's a lot of applications where you can have flow pretty low Mach number. The velocity of the fluid approaching a body is called the, here's this, and is denoted by this symbol V or U. Here's my object. Maybe it was my automobile. What do you call that? C? They talk about a free stream velocity. It's as if the stream over here is far away and it's not affected by the object. And so you think about the large flow field coming in this small object in it. And so they use this term free stream velocity. If you're not familiar with fluid mechanics, it's like, why'd they pick that? I don't know. I'm trying to explain it to you. It's far away. And so the presence of the object affects the flow velocity in the vicinity of the object. Okay. A body is said to be blank if there was a conscious effort to make it align its shape with the anticipated streamlines in the flow. You can see sometimes if somebody had some design intent behind an object. They anticipate the flow to go over around the object. If there was some effort to align the shape of the body with the anticipated streamlines in the flow, what would you call that? A bluff body or a streamlined body? That's really what a streamlined body is. It's easier to force a blank body through a fluid. Is it easier to force a bluff body or a streamlined body? Streamlined body. That's why they streamline it. The force a flowing fluid exerts on a body in the flow direction is called, so here's our free stream velocity profile, right? Here's our object. There can be a force in this direction, in the flow direction. Isn't that in the flow direction? Isn't it? What is this direction? Perpendicular to the flow direction. We're not talking about that force. We're talking about this force in the flow direction. What would that be called? What type? Is it called the punch, the push, the fall, the drag, or the mosh force? It's a drag force. Right? And then guess what the opposite is? Well, first of all, you have an object, you have that free stream approach velocity, V, and you get a net force on it, FD, and that net drag force can be because of pressure distribution as well as skin friction drag. So first of all, think about the pressure. It'll be high on the front end and low on the back side, right? That can give a net component to the drag force. In addition, you have the fluid flowing over, and it's always exerting a shear stress at the surface because of the viscosity, right? Because of the shear stress, that's a skin friction drag. So both of those components add up to give you the total drag. It's the skin friction due to viscosity and the pressure. What's the difference between these two? This is always perpendicular to the area of the object, and the skin friction is always aligned, tangential to the object shape. You can have separation, and often streamlined objects try to avoid separation. So if I have this object right here and I want to push it through the air and have a minimized drag force, how could I streamline that object? Well, take that object, maybe add something to the front of it to help it split the flow, add something to the back of it to help it, the flow reattach afterwards, to come back together. If you looked at the flow field around this object, you might find that the flow has a big wake region. And maybe even up in here, because it's blunt, it separates and throws around. There's separation region in here. So both this wake region and the separation region is bad. So you would try to minimize that by adding something in the front and then in the back, and hopefully minimize the wake and avoid any separation. All right. The drag coefficient, C sub D, what is that? The total drag force divided by 1/2 rho V squared times A. And what is that A? Do I go and get the sum of the area over this object? Is that what that A is? No, it's not. What is that A? It's that projected area. So it's the silhouette area. So sometimes I'll put projected on it. A lot of times people just put A, and you need to know what it means. So you look in the direction that the flow is coming at the body, and then you just look at the silhouette. The velocity of the fluid approaching a body is called the free stream. We already did that one. Give an example of an axisymmetric flow over a body. Anybody? This is military application, but here's a bullet. If you look at a bullet, you have an axis, and you can revolve that object around. So if I take the top half and just revolve it around that axis, isn't it an axisymmetric object? Yeah. All right. That's a good example of an axisymmetric object. Is an automobile axisymmetric? No. Can anybody think of another axisymmetric object where the flow is, supposed to be aligned with the axis of the object? The what one? Did you say a bomb? Ball? Sure, ball. Missile? Yeah, objects like that. A lot of engineered objects are supposed to be axisymmetric, stay aligned. Maybe they have fins or feathering or something to keep them. Give an example of flow over a bluff body. The old semis, I don't even know if you even saw those semis in the 60s and 70s. They were basically a plywood, sheet of plywood or two in the front. That's it. And it's like, you're just pushing and the cab right here and the window right there and the engine all under here. I don't remember where they put the engine. And the tractor trailer back here, right? The 18-wheelers. I guess they were really easy to drive because the driver's looking right down. They can, see immediately right there. But what did they start to do? They started to push those out and make them even the glass things. And then actually the trailer part was higher. Then they put the fairing up here. And now they do a lot of things with the skirts underneath. And actually in the backside they put some skirts and stuff, you'll see. So it used to be very bluff, and they've been trying over the years streamline those devices, those tractor trailers, rigs. Only time average force exerted by the fluid on an axisymmetric body aligned with the flow is the drag force. That's true. So if you have an axisymmetric, right, and it's just going to have, the time average is just going to be a drag force on it. Now, if I have an axisymmetric ball and I give it some spin, the spin just changed it, right? Because the flow on the spinning object, the spinning ball, will try to, because of no slip on the boundary, entrap and bring down more flow on the bottom side where it's spinning and less flow up top. Hence, it'll go a little faster, hence the ball will spin, will have a net force, not just in the drag direction of flow, but also it'll go typically, actually it'd spin that way, it would go that way. It would pull it. That's why pitchers, baseball players throw with spin. Do they put a spin on the basketball in the air when they're passing between each other? Probably not to make it dive or fall or have. Probably if there's a spin, it's due to when it hits the floor or something, or easier to catch or how the way it comes off, but not aerodynamically to change its trajectory in the air. But a baseball just changes the direction in the air. Okay. Any other objects? How about in tennis? I think it's primarily to when it hits the ground, right? Or is there enough time for it to have a curvature in the air? Tennis? When you really hit it with spin? Okay, that'll fake out your opponent. I don't play tennis, so. Pool, when you're hitting the billiard ball, you have backspin, topspin. But mainly that's to affect what happens to it after it hits the bank or hits another billiard ball, not really to interact with the air. It's interacting with the felt on the table, so that's different, slightly different. But does anybody think of another example? We have baseball, and we have tennis. Soccer, oh yeah, they really do curve a lot. Having these, boom, that's incredible how much they curve. If you know how to kick it right. So soccer is a good one. Is there any other balls you think of? Bowling, that's an interaction with the planks, right? So that's not so much the air the fluid that it's flowing through, but you're right. Another one? Wiffle ball? Yeah. Okay. Okay, lift is in the opposite direction, perpendicular to the flow. So not opposite, it's really normal, abnormal, aligned, parallel. No, it's normal or perpendicular to the flow direction. That's the lift. So this is a quick little problem. If you have a calculator, let's go ahead and solve this one. An object is oriented at an angle of 20 degrees. Here's our angle, 20 degrees, with respect to the flow direction. The net pressure and viscous shear force acting on the object is a net force of 750 newtons, and it's acting at an angle with the flow direction of 25 degrees. So there's two angles. One, it's the flow and the axis of the object. The other is the flow and the direction of the net resultant force on the object. See that? There's two angles. Okay, so one of them is 20 degrees, one of them is 25 degrees. Calculate the drag force on this object and the lift force acting on the object. So you go ahead. All right, so what did we calculate? That the drag force, that's the force in the direction of the fluid flow, aligned with the direction of the fluid flow, comes in at what, 680 Newton? And the lift force is in the direction perpendicular to what? Perpendicular to the axis of the object or perpendicular to the flow direction? Which one is it? It's in perpendicular to the flow direction. So that one comes in at 317 newtons. So which angle is never used? The 20 degrees is never used. So that's called the angle of attack. Okay. Oh, it'll definitely affect the lift force and it'll affect the drag force, but often they show you how it affects them by plotting, changing the angle of attack and how it affects the lift. But the lift always is perpendicular to the direction of the flow. So we have lift force, FL, lift coefficient. Oh, we could do that just like our drag coefficient. We have to normalize it. Let's normalize it by 1/2 rho v squared. But I need an area. And so what area do I multiply in the lift coefficient? Well, if my object is made for lift, it's usually very streamlined. True? And think about a wing, right? It's very streamlined, and I want it to generate, here's the flow direction, a large lift. So would it make sense to use some silhouette area, or would it make sense to use some area that is in perpendicular to the direction of lift? And this is the plan form area. This area, what do we call that? Silhouette area. So the area here is the plan form area. It's looking down from the direction that the lift is occurring. It's that perpendicular area. Okay, so yes, C sub L, the lift coefficient, and C sub D, the drag coefficient, typically have different areas. The blank force is the force a flowing fluid exerts on a body in the flow direction. Drag, not draft, drag force. The blank force is the force that the flowing fluid exerts on a body perpendicular to the flow direction. Lift. Drag is caused by two different effects. Which are the two effects for the drag? Which one? Pressure and friction. What about the lift? Is there a viscous component to the lift? Nope. It's just going to be the pressure. Okay, terminal velocity. I take an object and I drop it in the fluid. It could be a ball. It could be some teardrop shaped object. That doesn't look too much like a teardrop, but there it is. And it's going to reach some velocity, which is called the terminal velocity. What is that terminal velocity, v sub t, or v sub t? How do you calculate it? It's when you don't accelerate anymore, right? So when it's not accelerating anymore, what is the sum of what equal to 0? The sum of the forces in the direction that it would, if they were not equal to 0, it would accelerate, right? Well, it's in the falling direction. So what forces do I have on my object? Let's do a dot for a free body diagram. Free body diagram, free point diagram. A lot of these free bodies are free points, right? You ever notice that in statics? Oh, we're going to introduce the free body diagram, and for the whole chapter it's a point. That's not much of a body. But anyway, what forces act on this body? We have gravity, its weight, and we have the force drag, and there could be one more if the fluid has some significant density compared to the object. For example, if I drop in a piece of cork in water, what do you think? It's not even going to sink. What's it going to do? Float. Buoyancy. So we could have another one, buoyancy. So those three typically you need to count for. Okay. So you have the buoyancy, the drag, and the weight. And when they sum to equal to 0, that'll give you the terminal velocity. So let's do this. What is the buoyancy plus drag is equal to the weight? How do I calculate the buoyant force? If I could just take this class called fluid mechanics, I'd learn how to do that. You take the weight of the fluid that's displaced by the object. So you take the volume of the object and you multiply by the density of the fluid. That gives you the mass of the fluid that's displaced by the object, multiplied by g, and isn't that r? Okay. Over here we'll put weight. What is the weight of the? It's the volume of the object. It's the density of the object, and g. The only difference between the body force and the weight is either you're going to use the density of the fluid, which seems abnormal, like what? That's Archimedes' principle. Or you use the density of the object in the weight. Okay, but how about the drag force? This is the new one. So if you wanted to calculate the drag force, somebody just said, hey, I'm going to have the drag coefficients equal to the drag force times 1/2 rho v squared times a. So the drag force, just like unraveling the drag coefficient, is c sub d. That's a bad looking c. C sub d times 1/2 rho v squared times a. So that's what it is. It's the drag coefficient, 1/2 rho v squared times a. A lot of times, we're going to talk about it again because it's so important, we find that this drag coefficient plotted goes c sub d as a function of Reynolds number. It gets down into this region right in here. When it's flat, what does that mean about the drag coefficient in this flat region? Reynolds number independent. It's a constant. And so for a lot of cases, bluff bodies especially, it's a constant. So what we find is the drag force is proportional to the speed squared. It's proportional to v squared. Drag force is proportional to v squared. So this would allow you to calculate v. V would be some density of the object minus density of the fluid times the volume of the object times g divided by the c sub d, 1/2 area, the right area, the silhouette area, and then take the square root. Would that be my terminal? Sure. Did I miss anything? So you could calculate the terminal velocity. Stokes flow, it's low Reynolds number flow. When you see this term Stokes, in honor of Professor Stokes, I don't know exactly much about him. You know that it's low Reynolds number, viscous dominated, and you often find that the drag coefficient on a log plot is a straight line. It's a constant over the Reynolds number. That's the classic example. It's constant over a Reynolds number. So this would be for like spheres, cylinders, and cross flow, and some other objects. It's Stokes flow. The drag force is defined in terms of the frontal area for bluff bodies. True or false? The drag coefficient. True? The drag coefficient is defined in terms of the plan form area for slim bodies such as airfoils. That's actually true too. They can change it around, so you have to be careful. Okay? Because if you have a very slim body, an airfoil, you just have to be very careful how they define it. Okay? Remember, the drag force can be made up of two components. The pressure and the friction. Which one would typically dominate? It's going to be the friction component dominate. I don't have a large weight. I don't have a lot of separation. And so I don't have a high pressure on the front and low pressure on the back. So yes, this is true. The plan form area of an object is the area, outline or silhouette of an object viewed from above. So if the flow is coming in this direction, that's my object. It's viewed from above the object. True. The chord of a wing is, what is the chord? A line connecting the nose and the trailing edge, length of the top surface, circumferential length, perpendicular length, frontal length. Remember, if I just had an object, I'm going to draw a wing. They'll talk about the chord length. It goes from the tip to the other tip. It's a length. Straight line. Okay, so it's A. You're reading a textbook, right? Good. Which statement is true? Friction drag is a strong function of viscosity and increases with increasing viscosity, or weak function, blah, blah, blah. Which one do you like? Friction. The friction drag. Well, it's a strong function of viscosity, isn't it? I mean, it's proportional viscosity. So let's get rid of the weak. Get rid of that. Now, what about, does it increase with increasing viscosity or decrease with increasing viscosity? Which of those two is correct? It goes up with the viscosity. If the viscosity goes up, it goes up. So this one's right. Friction drag is 0 for a flat surface normal to the flow. Here's a flow. It's going around this flat surface that's oriented in a ridiculous way such that it creates a huge wake. So there's going to be a large drag force on this object, but it's going to be due to the pressure difference from front and back or the viscous forces. Which one do you think is really going to be large? The pressure. This is huge. What about this viscous, though? Well, the viscous is how the fluid is flowing. If you look at it, it's flowing around here. It's going up and up and up before it separates. So on the top side, it's kind of pushing the plate upward. That's the direction of the viscous flow. Is it in the direction of the flow itself? No. So basically, this viscous component is near zero, or is zero. Is zero. The friction drag, not the pressure drag, but the friction drag is near zero. It's all form drag. It's all pressure. When you have low Reynolds number flow, the drag coefficient is a constant over the Reynolds number. On a log-logs plot, C sub D versus Reynolds number, straight line down. How does the drag force vary then as a function of, let's say, speed of the flow? Well, let me do this. Let me go jump down here. So you have intermediate where actually the C sub D is a function of the Reynolds number, okay? So there's some transition region where it's a function of the Reynolds number, not just a constant over the Reynolds number, okay? And then often in high speed Reynolds number flow, the C sub D is a constant. It's Reynolds number independent. We already talked about how that drag force depends on the speed. In that case, because the drag coefficient's a constant, we go back, we say C sub D is equal to F of D 1/2 rho V squared times A. We find that F of D is C sub D, the constant, times 1/2 constant times rho constant, A constant, V squared. So all of this is just another constant, V squared. So the drag force at high Reynolds number, where it's Reynolds number independent, drag force coefficient's constant, is proportional to velocity squared. Well, let's go back here now and do it again for this one. So for the first one, you have that the C sub D is the constant divided by the Reynolds number. What is the Reynolds number for the, here, let me do this. C sub D is equal to the drag force divided by 1/2 rho V squared A. So F of D is equal to C sub D times 1/2 rho V squared A. Now let's use that the drag coefficient is a constant divided by the Reynolds number. What's the Reynolds number? Rho V, some length scale, let's call it L, over mu. True? Did I do that right for replacing the C sub D? Then I have the 1/2 rho V squared A. So the drag coefficient for low Reynolds number flow is, cancel that V with one of those V. It's like a constant times V. Make sense? All right. So I think we looked at some things like this before. You have a bunch of different objects, and you can get a single number for the drag coefficient. What does that mean about these objects? They're typically not streamlined, and we're out operating in a pretty high, no, it's Reynolds number independent region. It's not Stokes flow over these objects. Okay. It's interesting they even have things like, okay, frontal area of a semi-trailer, that's the appropriate area for the drag coefficient. And then they have with and without the fairing. What's that? That's the part over the cab that tries to help the air go over the trailer part. True? See how it changes it? That's why they added them. And they're out there. Minivan, even though it has a larger frontal area, it has a greater drag coefficient than maybe a more streamlined sports car. What would be a low end on a drag coefficient for an automobile, even like a race automobile? I mean, can they push it down to 0.01, 0.001, 0.0000? I mean, what is a reasonable low number for drag coefficient? It's really not much lower than 0.3, maybe 0.2. But you can look up. There's Wikipedia pages. They'll have them all listed. They'll even show you, okay, this year's, F1 has a drag coefficient of this range, and they can show you how they changed over the years. Small modifications. Maybe a 1930s pickup truck or something. Very high drag coefficient. But how high is very high? Maybe 0.6 or 0.8. All right. Okay. You ever see bikers? Do you ever see what they sometimes do around the wheels to help them? Yeah. That knocks down on the drag coefficient. Okay, we're out of time. Thank you very much for your attention. We'll pick up here. This is a very practical, I hope it's easy chapter for you, but you really want to walk away from this class having mastered external flow around common objects because it's so everyday common. Thank you.